I guess we can start. So, welcome back, everybody. And today we have a double session of talks here at the Prague Non-Commutative Geometry and Topology seminar series. And the first speaker is Adam Magee from CISA with a twisted real structure for spectral triples. Please, Adam.
Thanks, Alan. This is obviously a bit of a half-length talk, so I'm going to probably go a little bit quickly. If I'm going too fast, feel free to jump in and stop me. But the general structure of the talk will be split more or less into halves. The first half will be background and motivations. I'll talk about where real structures for spectral triples come from. And then the second half will be why we might want to modify that definition, generalize it to what we call twisted spectral triples, and what we've been doing with them. So to start off, in Con's approach to non-commutative geometry via spectral triples, often you start off with Clifford algebras. Today is no different. We'll start off by considering a complex Clifford algebra on which you always have a Z2 grading. And in particular, what we're interested in is a particular antilinear isomorphism you get by combining the Z2 grading with complex conjugation on the algebra elements. And this map, which we'll call kappa, is called the charge conjugation. So separately to that, suppose we have a Hilbert space, we can always define an anti-unitary operator on it. That's just, by that I mean an antilinear unitary operator. So on a Hilbert space, we can define an irrep of the Clifford algebra. If the vector space V is even, we'll take the whole Clifford algebra. Otherwise, if it's odd dimensional, we'll just take the even part to ensure that it's an irrep. In that case, then this anti-unitary C implements the charge conjugation map like so. And for that reason, I'll call C the charge conjugation operator. The Clifford algebra, the complex Clifford algebra, together with this kappa, notice that the charge conjugation map is an involution. We can treat this as a kind of star algebra, with the star structure, this unusual star structure being the charge conjugation implemented via C, such that little c and big C together give a star representation. And these representations can be classified. It turns out that they're more or less, well, they are equivalent to the real Clifford algebra of a signature PQ. This is quite an enrichment, actually. If you only take the complex Clifford algebra, it exhibits a two-periodicity. So there's only really two cases that you're interested in. Whereas in the real case, you have actually two kind of symmetries, this 1-1 periodicity, which is not so important for us, and this 8 periodicity, which is also called Bott periodicity. And what that basically means is that there are actually 8 cases that we're really interested in. The tensor product here is not going to be much of a concern. The reason is that, let's say, the representations of a C-star algebra are more or less given by your strong Rooter equivalences. And we always have that a C-star algebra is Rooter equivalent to its tensor product by some full real square matrix algebra. My God, this is terrible. Okay, imagine that that I can actually write properly. But yeah, so you can use this these periodicities via a gadget like this. This is called a spinorial clock. Along with some algorithm, you can generate all the Clifford algebras you want. But really, this 8-fold periodicity is what you want to keep in mind for later. So we'll shift now to looking more at manifolds and bundles rather than isolated vector spaces. The Clifford bundle, which will denote CLM, over a Riemannian manifold is just the algebra bundle generated by the cotangent bundle. It inherits this bundle structure, and the quadratic form for the Clifford algebra comes effectively from the metric. In here, the metric lifted to sections of the cotangent bundle. A Clifford module over a manifold is a finitely generated projective bimodule, which we'll call this fancy S. left modulo over sections of the Clifford bundle, right over continuous functions over the manifold. And for some complex vector bundle, regular S, this fancy S will be just the sections. And in fact, for reasons which will probably become obvious, this complex vector bundle is called the spinor bundle. So we're interested in the case where our fancy S Clifford module is irreducible. And that happens, incidentally, exactly when S is a Morita equivalence bimodule. That is to say, it implements the Morita equivalence of these two algebras, these two C-star algebras, sections of the Clifford bundle and the continuous functions. And in that case, so long as the manifold is equipped with an orientation, this combination of the orientation and the Morita equivalence bimodule S is called a spin C structure, and the manifold is a spin C manifold. The reason we're interested in spin C structures in particular is because if we have a spin C manifold, then we're guaranteed to be able to define a Dirac operator, which we'll come to shortly. So for reasons which are kind of complicated, it turns out that you can strengthen this spin C structure into a spin structure with the addition of just an anti-unitary operator C. Again, this should all be sounding kind of familiar. C on the bimodule. And you want that for what concerns the sections of the Clifford bundle, it really just implements the charge conjugation. So this is really taking it's just the same charge conjugation operator that we've seen before. So the charge conjugation operator is this extra ingredient which takes you from a spin C manifold to a spin manifold. And I mean, I'm a physicist by training, I guess. I know there are geometric reasons, abstract mathematical reasons why you might be more interested in spin than spin C, but for me, spin is what you want if you want to talk about uncharged spinors, for example. So we'll shift gears a little bit. I mentioned Dirac operators before. So as before, we'll have an algebra, C-star algebra, represented on a Hilbert space. So what I'll call a generalized Dirac operator by this D is just an unbounded self-adjoint operator with compact resolvent, such that its commutator with the representation of the algebra is bounded. And in that case, via this what's called bounded transform, we can take the unbounded D and spit out a bounded F Fredholm operator, such that we get our AHF pre-Fredholm module. Pre-Fredholm modules are useful because they give classes in K-homology. And because any class in K-homology can be obtained via this bounded transform, you can just deal with the Dirac operator rather than with the Fredholm operator, which is much harder to work with. And so we end up with the spectral triple, the C-star algebra, pre-C-star algebra, the Hilbert space, and the Dirac operator, motivated as an unbounded case cycle. Of course, you can always just start off with a spectral triple from the beginning, but I think this approach gives you a little bit of, I mean, at least if you're familiar with this sort of stuff, a little bit of intuition for where all of these come from. So now, if we require that our algebra carries an involution, then we can add in an action of the real Clifford algebra. And what I mean by that is we have a Hilbert space, we have an algebra, we want to represent the real Clifford algebra on the Hilbert space. But remember that the real Clifford algebra, the representations are equivalent to those of the complex Clifford algebra with an involution. And in particular, when that involution is the charge conjugation map, it's implemented on the Hilbert space by a charge conjugation operator. So what we can do is say that this charge conjugation operator also implements this involution on the algebra. And in that case, what you get is an unreduced KR cycle. The issue with an unreduced KR cycle is that the representation of the Clifford algebra is not irreducible. But what you can do is reduce it via a particular procedure down to some dense subspace on the Hilbert space, such that all of your algebra, your Dirac operator, your grading, if it's there, they have the same properties as before, more or less. But now you have an irrep of the real Clifford algebra. But rather than signature PQ, we have signature J0 or 0J, where J is just P minus Q. Mod 8, of course. So here you can see, as before, our Dirac operator, self-adjoint, unbounded, blah, blah, blah. This is exactly as it was before. Antilinear isometry, implementing tau. Tau here is the involution on the algebra. When J is even, we have a grading. And here, these mysterious signs basically come as a byproduct of the reduction process. You can think of them as a kind of imprint of the original full representation of the real Clifford algebra. This is what you get left over. And indeed, these three signs determine 8 cases. Those 8 cases determined precisely by J. Oops. So now we'll just completely change topic for a moment, put that all to one side, and we'll talk about something that's, okay, maybe not completely different, but quite different. Start off with von Neumann algebra A, represented again on a Hilbert space. Importantly, that we have a cyclic separating vector. And then it turns out this is, in a sense, the main result of Tomita-Takasaki theory, that you can define an antilinear isometry, which I've denoted here by J, such that J, via conjugation, maps the algebra to its commutant. From here on, this prime denotes the commutant inside B of H. And of course, I'm being quite fast and loose with representations of the algebra, but you can always assume that the algebra is being represented inside B of H. So this is quite important because in this case, in the case of the reduced chaos cycle, even though we've put everything in algebraic terms, there are some points where we're still relying on the commutativity of the algebra. So what we want to do is combine these two ideas, the reduced chaos cycle and the modular conjugation, to get a real spectral triple. And you can see that this is basically the same as a reduced chaos cycle with the addition of this point 2. And the reason that this is important is, first of all, this is pretty much, this is the condition that's coming from, let's say, inspired by Tomita-Takasaki, where we want J to commute with A, to be in the commutant. And then this condition here, where does this come from? Well, it turns out that if you want your Dirac operator to be a first order differential operator, which you do, in algebraic terms, with respect to functions, it's equivalent to requiring this for two functions f and g. But the trouble is that this only makes sense when f and g commute. So if you just replace these by algebra elements, it no longer makes any sense in the non-commutative context. But of course, if you replace g here, not by b, but by jbj, which does commute with any a, then everything works out nicely again. And maybe these conditions will also become a little bit clearer in the next section. But this is, in a sense, our starting point, a real spectral triple. And J here is what I will refer to as a real structure for the spectral triple. So successes and limitations. The framework of spectral triples give a huge number of examples. One of the most famous ones, one of the examples of a non-commutative space, the non-commutative 2 torus. Of course, some people just refer to this by the C-star algebra in the Hilbert space, but you can also give this a metric structure, which is more or less a non-commutative analog of the commutative 2 torus. And in fact, you can also give it a real structure and a grading. We'll sort of come back to this later if we have time. Other examples are matrix geometries. These are very important in the context of trying to do gauge theory with spectral triples, where the main object is an almost commutative, what's called almost commutative geometry, a product of a manifold with a matrix geometry like this. And then lots of other examples coming from geometry, coming from physics, coming from really pure maths. You can see we've got fuzzy spaces, Q-deformations, Moyle spaces, what you can read. But the problem is that the vast majority of cases are not real. They don't admit a real structure. They're not real spectral triples. And you might say, okay, fair enough, that's fine. If a real structure just indicates some kind of spin structure, not all manifolds are spin manifolds, So why should that be a problem? Well, while that's true, there are some cases where you would really like there to be a real structure, and yet there isn't. And so it's helpful to try and expand this notion also because it's very powerful. These two in particular, the requirement that the Dirac operator be first order is something that you want in a lot of cases. So you really would like to have this technology for as many cases as possible. So one case in particular that we'll look at where this will come in handy, or where this will be very relevant, is conformal transformations. So if we start off with a manifold, it doesn't have to be spin, but let's take it spin. Then a conformal transformation of the metric just rescales your metric by some real function. This in turn gives a corresponding transformation of the Dirac operator like so. Now, if you just make a one-to-one swap in the non-commutative case of your generalized Dirac operator with k dk for k some positive algebra element, this doesn't actually give a spectral triple anymore. And the problem is that the commutator of d with a being 0 doesn't imply that the commutator of k dk with the algebra is 0. Sorry, 0 is bounded. Oops. Yeah, that's also true on this side. So that one way that you can get around this is by using what are called twisted spectral triples. And in the twisted spectral triple case, what you want to do is replace these commutators by twisted commutators. So a twisted commutator, which will denote like so, is given by AB, in this case, minus not BA, but rho of BA, where rho is some map, usually take as an automorphism. Oops. And in this case, if you require that the bounded, sorry, that the twisted commutator of d with a is bounded. So if you require this, then on the twist, with a twist, the automorphism coming from this k, that is bounded. But the issue with this approach is that it really requires a lot of very dramatic changes to the structure of one forms, because these d commutators of d with a, oops, also generate, they generate the space of non-commutative one forms. So let's say the one forms in the non-commutative setting. And even if this reduces in the normal case to what you want when everything is commutative, you do lose a lot of very important theorems by making this pretty drastic change. So the question is, can you make a different alteration to fix this? And it turns out that you can. If you assume that your original spectral triple was real, then instead what you can do is, rather than taking k dk, you can take the opposite, jkj inverse, jkj inverse in the commutant. And of course, in the commutative case, this is exactly just k. And in addition, you have this twist operator nu here, and you can see again in the commutative case, jkj inverse is just k, so we have k inverse k. This is just an identity operator. And then your spectral triple with respect to this dk really is a spectral triple. It really is, the commutators are bounded. But now we have these modified relations. So here you can see this modification here is a modification of the first order condition from before here. But now we're applying a particular twist to the outer commutator, leaving the inner commutator safe. And here we're also implementing this twist here in the commutation of d with j. So the question is, can we use this as a blueprint for something more general? Yes. And you end up with a spectral triple with twisted real structure. And now we have a J, our antilinear isometry J, and nu, some twist operator, together giving a new twisted real structure. And at least in our case, the case we're most interested in is when nu really does implement an automorphism of the algebra. Again, we have the same commutation relation, the same twist on the first order condition, whoops. And also, usually we'll take some simplifying assumptions like this, what's called regularity condition, some commutation with the grading if it exists. Actually, in the literature, most of the time the twist does not appear in the commutation with the grading, but for reasons I won't get into, I think it should be there. So I guess I should stop at this point to ask if there are any questions. I know we've blitzed through a lot, which can make it both easier and harder.
Adam, can you come back one slide?
Yes.
Okay. So I wanted, so this epsilon second here will be basically the same sign that you have for the computation of J and the grading on the spectral, like in the classical case, so to say, right?
It
it's
depends.
not.
It depends. So for example, for the case of the conformal transformation, it's the same sign. All of the signs are the same. So you really have the same KO dimension. But in some cases, it's not quite so clear that that has to be the case or that that should be the case. So in principle, they can be different. The really important thing is just that they are signs, that you do have these commutation relations up to sign. Okay, so I'll keep going. Another nice example comes from Hodge-Durham spectral triples. Before I actually talk about those, I want to give a little bit of background. You'll have to forgive me again for the drawing. So what I've called here the zeroth order condition, this is equivalent to A being its commutant by a real structure. You can see this is equivalent to the first order condition, where here we have one forms as before. It's also possible to define what's called a second order condition in this way, but I'll talk about that in a moment. What's important is that these two conditions here are equivalent to this one. And these three are equivalent to this one, where here we're defining this, I guess you could call it non-commutative Clifford algebra, or a Dirac Clifford algebra, or however you like. Usually it's actually just called a Clifford algebra, as the C-star subalgebra generated by the algebra and commutators of D with the algebra. And this is just the non-commutative version of sections of the Clifford bundle. It plays the exact same role. And if you turn these inclusions into isomorphisms, you actually end up with these cases above, which we've called spin and Hodge. So here we're saying that there's some root equivalence, there's some bimodule which implements root equivalence of this Clifford algebra and the C-star completion of your star algebra. And in the Hodge case, it's a root equivalence of the Clifford algebra with itself. And it turns out that the motivation for the second order condition is that one of the most famous spectral triples, apart from the canonical spectral triple of a spin manifold, which we kind of touched on, is the one for the standard model. So I mentioned before that in the context of gauge theories, you have almost commutative spectral triples, which are the product of a manifold with a matrix geometry. It turns out that for the one which gives the standard model of particle physics, or at the classical level, the matrix geometry satisfies the second order condition by accident. And in fact, even stronger, it satisfies this Hodge condition. So the main motivation for this paper, which I wrote with my supervisor, Ludwig Dombrowski, and our collaborator, Francesco D'Andrea, is to investigate when this Hodge condition can exist on manifolds rather than just on matrix geometries. So to do that, we looked at the Hodge-Durham spectral triple. So if you have a manifold, of course, we've already seen one way to talk about it in terms of spinors. So you take your Hilbert spaces coming from the spinor bimodules that we defined before, but there is another way to do it via via differential forms, complexified differential forms in a way that's kind of blind to the spin structure. But you can recover this if you start off with the canonical case. You can recover this, where again we have the L2 forms, and now our Dirac operator here is just coming from the Durham differential, really, and of course the same algebra as before. This spectral triple admits two gradings in even dimensions. The one coming from the degree of forms, and this other one coming from the Hodge star, which I won't talk about so much here. But in addition to that, you can define two natural antilinear isometries on this particular spectral triple. One is just complex conjugation. Yes, Anna.
One slide before again, please. So you are saying that basically there is some reconstruction theorem for from this data, basically. So from the spectral triple of the Dirac complex of Riemann manifold.
Not quite. What I would say is that, as I'm sure you know, and if you don't in the audience, there's a reconstruction theorem for spin C manifolds, which more or less follows the what I described in the first half of the talk. There's no reconstruction theorem, as far as I'm aware, for more general cases of Riemannian manifolds. But if you do have a spin C manifold, you can recover this equivalent construction in a way that doesn't rely on spinors.
Okay, thank you.
Yeah, and so in fact, this Dirac operator you obtain from the normal Dirac operator in that case. So yeah, continuing, the reason that we're looking at the Hodge-Durham spectral triple in particular will become clear in a moment. But yeah, there are these two natural antilinear isometries, one complex conjugation, the other which reverses the wedge product on forms and also gives complex conjugation. The first one is a real structure. It doesn't implement the Hodge condition. It actually is kind of trivial. Indeed, it's a real structure that comes if you combine this with gamma deg, the grading from the degree. This monstrosity is actually just the charge conjugation, the honest to God charge conjugation that we saw before. This one, the origins are a little bit more mysterious, but actually it turns out that if you look at CLDA, the Clifford algebra, the double commutant is of a Neumann algebra, and this J is just the Tomita-Takasaki operator on this von Neumann algebra extended to the whole spectral triple. And this one isn't a real structure. It doesn't commute with the Dirac operator, but it does implement the Hodge condition, which is why we're looking at this case. So you can see it doesn't operate. It doesn't commute with the Dirac operator, but it does commute with the Dirac operator up to this twist. And it turns out that this particular choice of twist operator with J gives a twisted real structure. It's not too hard to see. I mean, by design, it satisfies the commutation relation. The other main modification is the twisted first order condition, but because this twist is involutible or it's somewhat mild, the twisted first order condition just reduces to the ordinary first order condition, which J already satisfies. The grading and the twist, the J, they all commute. So everything works out nicely. So now we're approaching the end, thankfully. I'm sure you're getting a little bit tired of the rapid fire facts, but it's nearly over. I'll talk about a little bit of other work that we're doing. One extension of this idea of twisted real structures is multi-twisted real structures. So if you've got one twist, why not add more? the idea is you can decompose the Dirac operator however you like, and to each of these decompositions you attach its own special twist, and then you weaken that the twists implement an automorphism of the algebra to now only implement an automorphism of bounded operators. And in that case, all of the other conditions are basically as they were before, except let's say with respect to the decomposition, the only real exception is the first order condition. If you don't have an algebra automorphism implemented by the twist, then actually you now need two different first zeroth order conditions, one for the twist one way and one for the twist in the opposite way, the inverse way. And one neat motivation for this is if you take the non-commutative torus, which we saw before, what you might want to do is do a kind of partial conformal transformation. You do or a multi-conformal transformation. You leave the first part of the Dirac operator invariant, but you conformally transform the second part. And what you end up with, at least in the commutative case, is a transformation from the flat 2 torus or n torus to an asymmetric curved torus, one which has non-zero scalar curvature. So that's kind of neat. There are other uses for these multi-twists, which I'm currently investigating, but are pretty early doors, so I don't want to get into too much detail. Another big project, I guess, that I've been working on, recently submitted, is about gauge transformations. So I mentioned before, gauge transformations for spectral triples. The issue is that the way that gauge transformations are implemented for spectral triples is via Morita self-equivalences that are ultimately implemented via unitary endomorphisms. And these don't naturally lend themselves to this kind of twist. So what you need to do is actually use a little bit of the technology coming from twisted spectral triples, those twisted commutator type spectral triples I mentioned before, so that the fluctuation, the gauge transformations of the Dirac operator, which you get, or gauge transformations of the gauge potential rather, incorporate this twist. And this can be done. It turns out that this can be done, provided absolutely that the twist is self-adjoint. It seems like that's really absolutely necessary. And it seems like if you want to use the spectral action, you will also need that the twist is unitary. And that's quite restrictive. But like I said before, I'm also looking at sort of directions that these two are pointing towards, but are very, very much early on. I don't want to say too much, because if it doesn't work out, I'll make quite the fool of myself. Anyway, that's it. References for each section for those who are interested. Otherwise, thank you very much for your attention, and I'm happy to answer any questions now or after the next talk.
Let's thank Adam. And is there any question? Okay, if so, I may have a question. So, Adam, do you have some other example in mind that can work out of some spectral triple, or some example of spectral triple, which doesn't have, the classical, which doesn't respect the classical first order and second order condition, and might need this twisted real structure?
Yeah, funnily enough, there are not that many. And in fact, they seem to be very rare. Of all of the examples that I found where these twisted real structures are quite useful, a lot of the time they incidentally end up being involutions, in which case you get the ordinary first order condition back. Okay. It seems to be a very robust kind of condition. Off the top of my head, I can't think of any others apart from the conformal case that really make full use of the twisted first order condition. But that said, well, no, I'll just leave it there.
Okay, thank you. And okay, so is there any other question? Okay, so let's thank Adam again.